part 2 of our Unit 2 AP Exam Review Packet. So part 1 went through the first page. We're going to look at the second page, starting with logarithmic functions. So we have the template for logarithmic functions where we have some a value and then log base b of x. There could be other transformations that occur, but this is going to be the most generic form. And so if our a value is positive, we have a logarithmic function that has an asymptote at x equals 0, so on the y-axis, and our graph is going to be increasing and concave down. If our a value is negative, we can connect it back to transformations. We still have an asymptote at x equals 0, so the y-axis, but instead of it increasing, we're reflecting it over the x-axis, and so our graph is going to be decreasing. And this would be concave up. So a function is logarithmic if the inputs, or the x values, change proportionally as the output values increase in equal length intervals. We can also say the inputs change multiplicatively as the outputs change additively. So I do want to talk about a couple transformations. Here we're just going to go through pretty quickly. When we have a number that's being added or subtracted on the inside, if it is being added, then it is moving left. If it is being subtracted, then it is moving right. If we are adding or subtracting on the outside of our function, outside of parentheses, outside of that logarithm, if it's adding, we are shifting it up, and if it is subtracting, we are shifting it down. If we're multiplying by a number on the inside, that is a horizontal dilation. And for horizontal dilations, they're a little tricky. So if I had a whole number of 2, I would have a horizontal shrink by a factor of 1/2. I'm doing the reciprocal. If I had a number like 5, I have a horizontal shrink by a factor of 1/5. If it is a number between 0 and 1, so let's say it's 1/3, I would have a horizontal stretch by a factor of 3. So this one's a little tricky. If our number is outside, out in front, that is a vertical dilation. And this one's a little bit easier to remember because it makes sense in our brain. If we have a number like 2, 3, 5, anything bigger than 1, then it is going to be a vertical stretch. If the number out in front is a decimal or a fraction that's in between 0 and 1, so an example would be 0.25, 0.5, 1/3, 2/3, that would be a vertical shrink by a factor of whatever that number is. A negative out in front reflects across the x-axis, and a negative on the inside causes a reflection over the y-axis. And so if we have a general base understanding of transformations, that will help us kind of figure out what these graphs would look like, which also can help us with end behavior or asymptotes, or just in general what they look like. So for this one, I have a reflection over the x-axis. I have a vertical stretch by a factor of 3, and it is going up 1. So I'm just going to try to write that really small here. Reflect over the x, vertical stretch by 3, and up 1. So for this logarithm, if it started off without the negative, that 3 would be causing a graph that looks like this, and then it's getting shifted up 1. But since I have that reflection, my graph will end up looking something like this. And it crosses my x-axis at a higher number because I shifted it up 1 compared to this one. For this one, the only transformation is that it is going right 3. And so if I were to graph this, instead of my asymptote being at x equals 0, my asymptote is at x equals 3 because I shifted it right 3. So my graph looks like this. My number in front of the logarithm is still positive, so it is increasing. For the last logarithm, it is a natural log. I have a reflection over the y-axis because of the negative on the inside, and I have a horizontal shrink by a factor of the reciprocal of 3, which is 1/3. So for this graph, if I'm reflecting it over the y-axis, it's going to be on the left-hand side here. And then I have a horizontal shrink. So if I'm shrinking it horizontally, I'm kind of compressing it this way. So it's going to appear a little bit taller, but not as much as like a vertical stretch. So my graph will look something like that. And so if I am asked about end behavior or asymptotes, if I can picture graphs like this, I can be more accurate with the end behavior. All right, the box underneath, we're looking at composition of functions. If we have this notation, we can rewrite it as g of f of x, so we can see what goes on the inside. And then for compositions, we always work inside out. It could be more than just 2. We've had some where we've done like 4 or 5. And then this one can be rewritten as f of g of x. So let's make up an example here. I have k of x, which is my table. I have h of x, which is my equation. Let's say we're going to do h of k of 2. So I want to start with the inside, which is k of 2. For k, I'm looking at the table. If my input is 2, my output is 5. So I know k of 2 is 5. So I can rewrite this as h of 5. And then for h of 5, I'm going to take this 5 and plug it in to every variable in my h of x function. So I want to make sure that I'm paying attention to the name of these functions. So I'm going to write it out because it is in the notes, but we could just type it in our calculator. So I would have something like that. And then when I type it in, when you're doing an exponent of 3, we want to use our caret button there. It looks like a little hat or a little arrow up. And I get negative 310.5. Last one on this page, we're looking at inverse function. So to find the inverse when given an equation, we want to switch x and y and then solve for y. So solve for the new y. When we have graphs, graphs are reflections over the line y equals x. That's what an inverse function is. We're reflecting it over that diagonal line y equals x. And then we know that the domain of the original function, f of x, is the same as or equal to the range of the inverse. And I'm going to write the inverse notation here. So our inverse uses still f and x, but it has this little -1 there. That's the notation of an inverse, which means the range of the original is equivalent to the domain of the inverse. And so if I look at this graph, we're going to say that there's endpoints here. And let's find the domain of, we'll call this f of x. So the domain of f of x is how far left and how far right. So it goes to -5 up to +5. So my domain is from -5 to 5. I am using brackets because I put closed endpoints on there. And then my range of this function of f of x is the bottom to the top. So how far down it goes to how far up it goes. And the very lowest point is right here at -3, and the very highest point is at +3. So my range would be -3 to +3. So I could take the time to regraph it across a line that is y equals x if I had to find the domain range of the inverse, or I could just know that if this is the domain of f of x, I know that the range, oh my gosh, of the inverse is the same. So the range of the inverse is -5 to 5. And then the domain of the inverse is the same as the range of my original. So I know that they are connected that way. We are going to finish up the rest of this packet. We got 2 more categories on the next page, so let's look at those. We're looking at residuals. So residuals is when we look at the actual output or the actual y value and we subtract the predicted y value from it. If the residual is positive, that means that the actual is bigger. So the predicted value is an underestimate. If the residual is negative, that means the actual is smaller and the predicted is bigger. So the predicted value is an overestimate. When we are looking at a residual plot, we want it to look random and completely scattered. We do not want a pattern. We do not want all of the residual points to be an overestimate or all to be an underestimate. We want it to be random, scattered, and pretty evenly dispersed. If this is true, then this would indicate that the model chosen is appropriate. So we have 2 residual graphs here. They are not connected to each other. They're about 2 different functions. This model right here, what I'm looking at is, well, I see a pattern. I have like a U-shaped in my residual points. Since I notice a pattern, that means that this model that was chosen to create this is not appropriate. And what I'm thinking is there was a linear function that was used and the residuals have this parabola shape. Since it looks like a quadratic, that is assigned to us that a quadratic model would actually be a better fit. So let's put that kind of small down here. Or a quadratic would be more appropriate than the one that was currently used. For this one, we're looking at, again, if it's random and scattered, and it doesn't look like there's a pattern. I have a similar amount above and below the line at 0 there. And so this means that whatever function model that was chosen is appropriate. Last one, we're looking at semi-log plots or semi-log paper. Semi-log paper has a scale that changes. So I'm going to do a quick little sketch over here. What happens is it starts off going by 1. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. As soon as I reach 10, my scale isn't ones anymore. So then it goes 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then once I reach 100, my scale is not tens anymore. Now it's hundreds. So I have 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000, and so on and so forth. And sometimes you'll see it as like 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. But our scale changes. So this is by ones, this is by tens, and these are by 100. The point of semi-log paper is we can take any exponential graph, and when we graph it onto semi-log paper, it appears linear. And so when we're looking at real life data, sometimes the values increase so drastically that we can't get an accurate picture of what's going on. That is why we use semi-log paper. We can fit more on a graph if it appears linear. So we're just going to make a little note here. Semi-log paper makes exponential graphs appear or look linear. And then at the bottom, there's some important vocabulary for this unit. And then regressions are still listed, but I did change. Now we have exponential and logarithmic regressions to consider as well.